Good day, everyone. Welcome to another ASEG Tech Talk. We're delighted today to be joined by Sebastian Wong from Geoscience Australia. Before I go through ASEG membership and today's speaker, I'd like to begin by acknowledging the traditional custodians of the land. The ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuing connection to these lands, water, and culture, and pay our respects to their elders, past and present. Thanks to our corporate members that have been supporting us the past years. If you're not a member of ASEG, I highly recommend you to become a member. You get free access to publications, especially Exploration Geophysics, which is a high-quality international technical journal. You get access to the Preview magazine, ASEG newsletter, ASEG special publications, and ASEG external abstracts from ASEG and AEGC conferences from 2001 onwards. We have a range of professional and networking development opportunities. You get reduced registration fee for the Australasian Exploration Geoscience Convention, access to conferences and events hosted by ASEG sister societies, short courses, technical and social events such as this one. We also have a huge range of online content, webinars, workshops, job advertisements. If you are in search for geophysicists, experts in the field, or geophysical contractors, you get access to that as well. And also you get recognition for distinguished contributions and service to the profession through ASEG's honors and awards. We have ongoing research and documentation of Australian exploration geophysics and geophysicists through ASEG's History Committee. Membership for students is free, and you get discounted membership rates for retirees and recent graduates. We also have an exclusive member-only discounted wines curated by ASEG's Northern Territory and South Australia bench. So today's keep in touch. We are on most of social media platforms: Facebook, LinkedIn, and YouTube. Today's talk will be recorded, and you have access to it through YouTube, our YouTube channel. So today's talk is by Sebastian Wong from Geoscience Australia. Sebastian is the 3D Geoscience Integration Activity Leader at Geoscience Australia, managing national collection and storage of subsurface data from geological and geophysical sources. His work contributes to constructing a continental geological configuration, cover thickness modeling, and provides key pre-competitive data for environmental management, resource exploration, hazard mapping, and geoscientific research. And with that, I hand over to Seb for his presentation.
And thank you, and everyone else who has helped organise this. Just to begin with, this presentation is heavily based on a presentation I recently gave at the AGES conference in Northern Territory. But I do have a bit of extra time, so I've added a few extra slides. So the main focus of this presentation will be on some work that I'm currently doing in what we call the Birrindudu Deep Dive, which is in sort of straddles the border between Northern Territory and Western Australia. So that'll be the main focus of this talk. So first off, I just want to acknowledge all the people that have contributed to this work. So wide range of people from different disciplines. So we've got a lot of people that have helped with the interpretation workflow, people who have contributed to the provision of the AEM data that we interpret, so the airborne electromagnetic data, interpreters themselves, and also just a lot of support from various people. I think Babak's done a welcome to country, but I'd also just like to acknowledge the people across Australia, the traditional owners of the land. We work at a national scale, so just want to pay my respects to the Aboriginal people across Australia. This work is funded by the Resourcing Australia's Prosperity Initiative, but a lot of this work started as part of the Exploring for the Future program. So it's a continuation of that work. And I'd just like to acknowledge all the geological surveys of the states and territories, because they have had input into this work as well. So when we talk about chronostratigraphic mapping, what do we actually mean? So Geoscience Australia has provided a national chronostratigraphic dataset, which has mapped key geological era boundaries. So that's the Cenozoic, Mesozoic, Paleozoic, and so on. And that's a national map known as our layered geology. So we work at that same chronostratigraphic resolution in our team, and what we do is we map the thicknesses of those things. Sorry, I'm just having trouble advancing these slides. Just one sec. So what we do in our team is just map the thickness of the cover sequences and the depth to these surfaces. So in the AEM, what we do is we map the geoelectrical features that we can interpret as these chronostratigraphic boundaries, and we delineate them in the dataset. We also map other things that are not sort of chronostratigraphic, so discrete electrical conductors, hydrostratigraphic information, and so on. And we also map things within these geological eras as well. So it's not strictly that, but that's our main focus. So just a 101 on AEM and the colour stretch that you're going to be seeing for the remainder of this presentation. So we're working with a resistive in the cooler colours and conductive in the warmer colours. Here's some sort of just a generalisation of some typical rocks. So we've got sands, igneous and metamorphic rocks in the more resistive end of the spectrum, through down to massive sulfides at the conductive. Sandstones are sort of moderately conductive, mudstones are conductive. But that's not always the case. That's a generalisation. So we can have the groundwater chemistry can play a big role in what the conductivity signature, as well as the degree of weathering. So just for a a real world example, in the bottom here we have a conductive horizon that's overlain by a more resistive horizon, overlain by a more conductive horizon. When we integrate the AEM with surface geology and boreholes, we get to see that we can start to apply stratigraphy to these features. So here we have the Nora Formation, which is a mudstone, and then we have the Carlo Sandstone, and then the Mithaka Formation, which is also a mudstone. And you can see those, that response that sort of correlates well to this up here as well. And this is typically how we do our interpretation. We bring in as much data sets that we can to inform our interpretation. So here's just a sort of a conceptual overview of how we work and what we're really trying to get out of this whole body of work. So we've already got an excellent understanding about the surface geology, and this is based on years of mapping from the geological surveys and the State and Territory Geological Survey and Geoscience Australia and predecessors. But how do we extend that understanding undercover and just look through that cover? So one way we can use AEM, it's a non-invasive, quite cost-effective way of mapping large areas to approximately 500 metres. We've got this excellent AusAEM data set that's flown at 20-kilometre line spacing or tighter across large parts of the country. And so we can interpret that to look at depth to some of those features that I mentioned earlier. But it is limited at depth. So how do we look deeper? Well, we can use boreholes, for example. Boreholes are an excellent point of truth, but they're expensive to acquire. They're sparsely distributed. So how do we fill in between these? We can use other geophysical methods. So here's just an example of using depth to magnetic anomalies. So this example is just showing like modeling the depth to tabular bodies in the AEM, in the magnetics, and we can use that to look at some deeper points. So what we do is we then take these depth estimates and we harmonise them. So we sort of standardise the format and we upload them into what's known as the Estimates of Geological and Geophysical Surfaces database. And then that becomes a excuse me, a one-stop shop for extracting those depth estimates and can feed into our cover modelling exercises, which this illustration is demonstrating. And that just really feeds into what we are planning to do as part of the Resourcing Australia's Prosperity Initiative, and that's building these surfaces across the country, and that's sort of more of a long-term vision. So when we interpret the AEM, we integrate it with a wide range of supporting data sets, such as the potential fields, surface geology, digital elevation models, boreholes, water bores, infrastructure, and so on. And then what that really does, it means that we get the sort of best or most comprehensive interpretation that we can get by considering as much supporting data as possible. And what we do is something weird happened with that animation, but what we do is we take information from that and we attribute it to the interpretation. So our interpretations aren't just lines. They actually store a huge amount of supporting information. So that's the confidence of the line placement. There's stratigraphic units above and below the lines, hydrostratigraphic information supporting, what supported the interpretation, a very valuable comments field, and a wide range of information. So what you're going to be seeing for the remainder of this talk is just mostly the fancy lines. But I just want you to keep in the back of your mind that those lines actually have a huge amount of supporting information stored with them, which I think is the real, the real value of this data set, because it can be filtered for various things, and it can, you can extract stratigraphic units and look to the depth of them and stuff like that. So to do this, we've had to develop a new workflow. This workflow operates on a range of, open source or freely available 3D software packages and GIS software. The outputs are not bound by any proprietary restrictions or limitations. So what that means is they can go into various software packages without any issue, and they can be directly uploaded into that ASEG database, which I mentioned earlier, which can be accessed on our portal. And they can also go into the 3D layers on our portal as well. So this workflow has been published. So if you're interested in that, you can have a look at that. But more recently, we've developed a online graphical user interface, which does the whole conversion part of our interpretation. So what this does is it runs validation on the interpretation. So it validates the stratigraphic units against the Australian Stratigraphic Units Database. It validates geometry of the interpretation and the input files and a whole range of stuff, and then exports the interpretations in a range of different formats. So that's available online, and it works in conjunction with our interpretation workflow. So there's Australia. It's a big country. We've got the AusAM. We're really lucky to have this national data set. It's just such an excellent data set. And so this is the AusAM and some other selected surveys I've put in there. And just to show you sort of where we're up to. So these are the interpretations that have been published using this workflow. They currently cover almost 30% of the country at 20-kilometre line spacing. They're available online through ECAT, which is our electronic data catalogue, where you can download standalone versions of these interpretations, but they're also available for download on eggs and the 3D layers on the portal as well. So what I'm going to do is I'm going to jump around some of these areas, but before I do that, I'm going to just focus mainly on some of the more recent work that we've done. So we're currently working in what's known as the Birrindudu Deep Dive, which is this bit up here. And we're working in the Officer Basin, and we've just kicked off some work in northeast Queensland as well. But the remainder of majority of this talk is really going to focus on that Birrindudu Deep Dive area, and then I'll just jump around to some of those other places. So let's look at this area in greater detail. So just some geological settings. So we've got the Archean to Proterozoic Tanimite origin. And then we've got some Paleoproterozoic base origins as well. So the Wanamian Milwindi origin, or the Hooper province, the Halls Creek and Lambu province, and the Aileron province just down in the southeast. We've got some Proterozoic basins. So we've got the Spiwa Kimberley Basin and the Birrindudu Basin right through the centre. We've got the Neoproterozoic to Paleozoic Louisa Basin, the Wolf Basin and Murrabba Basin, and this whole area was covered by the Kalparingi Large Igneous Province around 500 million years ago, which you can still see some remnants in the green there on the surface geology map. And then this whole area was overlain by a Paleozoic basin. So we've got the Ord Basin in the centre in the north, Wiseau in the east, and then the Canning Paleozoic to Mesozoic basin in the west. So what I'm going to do is so I'll just strip off that the surface geology. I should just mention that, as you can see, all those yellow sort of colours, their whole area is also covered in a lot of Cenozoic cover as well. So straight away you can start to see in the AEM, you can start to see like those big basins. There's the Wiseau, here's the Canning, and there's sort of the Ord and the Murrabba over the more resistive Proterozoic bedrock. And here's just the interpretation. So at the time of making this slide, I was almost complete. I still have like a line in the north to do, but it's getting there. So what I'm going to do is in here, I'm just going to jump around some of these areas and look at some stuff that we've seen there. So the first cab off the rank would be some stuff that I've seen that could help with mineral exploration. So we're just we're in this area in the study area. So we're just southwest of Halls Creek, which is off in this direction. This is the Olympio formation of the Halls Creek group in brown here. And if we look at if we bring in the mineral occurrences data set, we can see they're really concentrated in that Olympio formation. If we have a look at some of the potential fields, so in the magnetics, we can straight away see that there's this north, east, southwest structural trends through that area, and some of the mineralization lines up with that. We can also see in the gravity that there's potentially these things are associated with these high density rocks as well. And these are the typical data sets that industry would use to sort of do a first pass to get them into an area to look for targets. But they don't really give you a really good understanding about maybe the depth to some of these features. Well, they can, but boreholes can be more helpful. So I've brought some boreholes in here. They're very difficult to see, but there's some up here. But what that really shows is that they're quite sparsely distributed. There's whole areas where, we just don't have many boreholes where they're difficult to access. And this is where the AEM comes in, because we can really take away that cover now and look at, you get a better feel for what's happening in this area. So straight away, you can see these discrete electrical conductors. So there's these discrete electrical conductors that are associated with maybe some of these magnetic anomalies, and they're in the area of no mineralization. We can also see, I guess more of these discrete electrical conductors, we can start to get a feel for how the host rocks or possibly even the mineralization dips away from the surface. And you know, when we have infills, because we're looking at 20-kilometre line spacing, but when we have infill of data as well of AEM, you can actually start to really get a 3D sense of these things as well, to see sort of how they extend at depth. So this is showing just some of the interpretation, and these features can be filtered for in the data set. So there's a lot of commentary about, like, you know, what the nearby mineral occurrences are, how they have been considered as potentially geological and not inversion artifact or you know, an anthropogenic source. So there's a lot in the data set that you can drill into in these things. But if we just look at a specific mineral type, so if we just look at graphite, for example, so we've just come a bit further northeast, sorry, of where we were before. Just now we're not a bit north of Halls Creek. So we're looking at the Ticularum metamorphics, which is all up in through here. And we bring those mineral occurrences on just for the graphite. You can see that they're associated with the stratigraphy. They fall on the contacts between different stratigraphic units. There's a lot of faulting in that northeast, southwest direction, which these things are also associated with. And then we look at those potential fields, and you can see that they also fall on, you know, maybe the boundary of some of these dense rocks and sort of moderate density rocks, and along the structural trends throughout this area. We bring in the AEM, and what we can see there is some really interesting stuff. So along strike, that we can see the strike in the potential fields, we get these discrete electrical conductors. Where we have known graphite, we also have those discrete electrical conductors. So, you know, this is sort of helping us say, well, potentially there's undocumented graphite occurrences in some of these areas. There's this whopping big one down here where there's one known graphite occurrence, which is really interesting. But if we look up in this area just up here, so up strike of these graphite occurrences, we have a little discrete electrical conductor on this line. On a recent trip to the Western Australia Geological Survey's drill core library in Perth, that was organised by the onshore energy systems team here at Geoscience Australia, we actually pulled out one of these, a couple of these boreholes right in this area, and what we found was that there was this graphite-rich intersection from about 150 to 200 metres. And that correlates extremely well with this discrete electrical conductor that we can see in the AEM. And what that says is that, you know, some of those other discrete electrical conductors, could they also be graphite occurrences? This kind of observation really helps build a sort of a bit more confidence that what we're seeing could actually be graphite in areas where there's undocumented graphite. So graphite, you know, it's really important at the moment. It's used in high-tech, you know, high-tech sort of manufacturing and products. It's an excellent conductor. And the onshore energy systems team at Geoscience Australia are doing excellent work in just looking more at the graphite in this area. So I would definitely recommend keep an eye out for the work of Emma Grosjean working on the graphite in this area. So just some observations about the structures. So in this area we have a lot of folding. So we're in like the central part of the area of interest. We've got a lot of these folds in the Proterozoic Biraduda Basin, and we can just get a better feel for how some of these things sort of extend at depth. We can look at areas where there's folding, and we can see repeated stratigraphy either side of the faults, and we can actually map how these folds occur at depth. In this area here, in that trip to the Perth Drill Core Library, we looked at a borehole there that intersected sulfide mineralisation, and that wasn't far off this line, which has discrete electrical conductors in it, so that was quite interesting. And Up in the north here, we're looking at the Browns Range Dome. So on this western side of the Browns Range Dome, there's unconformity between Archean to Paleoproterozoic and sort of younger Paleoproterozoic rocks. And in that area, there's unconformity-related rare earth element occurrences and deposits. And so what we can actually do is get a better understanding about how that unconformity projects to depth as well using this data set. So we can really get a feel for how some of these sort of the limbs of these domes sort of extend to depth and track that mineralized unconformity at depth. So everything that I've showed in the past couple of slides really shows how this data set can be picked up by industry to use to constrain targets and broaden search areas. And it's not just for minerals, it can help to look for the extension of deeper sort of hydrocarbon traps or aquitars and aquifers for groundwater exploration as well. So sort of stepping out a bit in scale, looking at like a really large geological feature. So here we've got the Ord Basin. It's a Paleozoic basin that overlies that Ambrine Plateau volcanics that you can see in green on the surface geology. It's bound by Proterozoic rocks in the west, which I'll put the mineral occurrences on, which are quite heavily mineralized. And we know these rocks extend undercover as well. We have similar aged Proterozoic rocks on the eastern side of the basin. So how do we get a feel for the thickness of that basin down to those mineralized rocks undercover? The potential fields are really helpful for that. You can see some of the Ambrine Plateau volcanics. It's this really high amplitude, short wavelength stuff sort of petering out into this sort of low density area as well. So the gravity and the magnetics can give you a feel for that basin deepening. But how do we actually map that basin interface? We can look at boreholes, but again, the boreholes don't drill through that area, and there's very limited basement intersecting boreholes. And so again, this is where the AEM really shines. So we can have a look at the AEM in this area. What's really helpful here as well is that Ambrine Plateau volcanics forms a marker horizon, which because that was deposited right at sort of the start of the Cambrian, so it sort of separates the Proterozoic from the Paleozoic. It becomes a really good marker horizon for the base of the basin. But we can also interpret some internal stratigraphy within the basin. So for example, here we've got resistive Devonian sandstones within the Ord Basin that's overlying these older Cambrian limestones, which have quite a different signature, and we can map those internal stratigraphy as well. I haven't interpreted this bit, but it just sort of shows you how you can just do your own little interpretation in your head there, because it's just a perfect example of how we can actually see the basin geometries in the AEM. So sorry, I keep clicking, but it doesn't do anything. So here I've just put a bit more contrast on the interpretation to just show you how it shines and show you how we can really start to map the thickness of these basins and internal stratigraphy within. So yep, there's just those mineral occurrences again. But that was just for this area up here. But the same applies to the other basins, so the Wiseau in the east and the Canning in the west. I think what's really interesting is the Wiseau Basin is similar age, similar deposition environment as the Georgina Basin. And the Georgina Basin hosts some phosphate deposits at that basement unconformity. And so what I'm going to do is I'm just going to step out really quickly outside of this study area to some work that we did previously in central NT around the Dulce syncline. And so here we have, it's quite similar to what we were looking in the Ord Basin, but we can really start to map some of the, maybe parasitic folding within the basin and the thickness of the basin, and maybe some faulting as well. We knew that there was a syncline there from the excellent geological maps, but understanding that sort of subsurface geometry, this AEM data set has allowed us to see a lot more than we previously knew. And what's really interesting here is that there's a lot of base metal deposits in the south of the basin, and these phosphate deposits either side of the basin as well. So the phosphates in the pink and the base metals in this sort of light greeny blue colour. So really understanding that contact can show where these mineralized stratigraphy exist. Sorry. So we just jump back into the Birrindudu area. So just another, we're just in that sort of eastern Browns Range dome up in the sort of the left of the screen here. And we're going to look at the Paleo Valley. So the WASANT, the Western Australia, Northern Territory, Western Australia, South Australia, Northern Territory Paleo Valley dataset of 2012 did an excellent job of mapping Paleo Valleys across the sort of the western 2/3 of the country, but they didn't have this widespread regional AEM dataset to use for that mapping. And so here, what it shows is that we can really use the AusAEM to refine such maps. So I've just shown the intersection between the WASANT and the Paleo Valleys, and so the Paleo Valleys and the AEM. It's going to be busy, so what I'll do is I'll just highlight where those intersections occur. And you can straight away see this sort of like this conductive horizon, but to me, it truly does not look like a thick, incised, channel-like geometry. I've interpreted a lot of these near-surface conductive horizons to actually be weathering of that Proterozoic basement and not even like thick sediments. There are sediments here, but they are very thin across the top. And so what that shows is that maybe in this area, the Paleo Valleys have been over-mapped. So this really shows that AEM can actually be an excellent tool for mapping or revising of Paleo Valley maps. And that's in stark contrast to what we see in the central NT, where we get these thick 200 metre, 250 metre thick, 400 kilometre long, true, proper Paleo Valleys, which I'm going to step out and have a look at that in greater detail now. So we're going to start to move away from the Birrindudu now and just look at some stuff broader across some of the interpretations that we've previously done. So this is that area in central Northern Territory. It's quite a large area. It's about 400 by 300 kilometres. And you can see that widespread Cenozoic cover. So all these yellows and beiges and stuff are widespread Cenozoic cover. We have these outcrops, Proterozoic outcrop, and we can see there's potentially a change in what's happening underneath this cover by the age of the rocks. These little scattered outcrops sort of change across here. They're Proterozoic here and they're Paleozoic on this side. So what's causing that? Well, when we look at the AEM, we can straight away see that there's a stark contrast between this resistive Aileron province here and the Wiseau Basin in the moderately conductive rocks here. And if we interpret that as a fault, separating those two, and then start to look at other data sets to work out what could this fault be. And we look at the major crustal boundaries from Cauchy and Dublier. We can see there's the Wallora suture, which matches perfectly this thing pretty much. Just let you know that main figure is north to the left. So this Wallora suture is a it's a crustal scale feature. If we look at the 36 kilometre Auslamp, so the long period magnetotellurics, we can see that there's this conductive horizon along there. So that's been interpreted as potentially metasomatism. And it's sort of linking some of the Tanami gold region as well, that this big conductor under there. So what's really important is that these these features, first of all, we didn't know this Rellora suture came so close to the surface. So I'm calling this like a near surface extension of the Rellora suture. And these major crustal boundaries can bring mineralizing fluids to upper crustal levels as well. So understanding that this thing just sits under like 10 meters of Cenozoic cover, so close to the surface, is really actually has some mineral exploration sort of implications as well. What I also found is when I put the DEM on, there's potentially significant, there's a significant offset between the aileron province thrust over the Wiseau Basin. So it really shows that maybe this thing's neotectonic. There's been sort of relatively recent movement along this, meaning that this kind of information can be used for hazard mapping as well. Here's just some stratigraphy within the Wiseau Basin and the landed trough of the Wiseau Basin. It's the Hanson riverbeds over the Lake Surprise sandstone, and just showing how we can interpret some of that stratigraphy within the basins as well. So I just put the cover back on, and it just shows how we're starting to really build up a better understanding about what's going on under that cover in this area. Back to the paleo valleys. So as I mentioned before, here's the WASANT data set in those polygons. But when we look at this area here in greater detail with the AEM, you really get a better feel for what's going on here. So there's those paleo valleys that I mentioned earlier, the really thick, quite extensive paleo valleys. And then if we bring that WASANT paleo valley data set back on, so sorry, this is just our interpretation of using that sort of integrated workflow, but then bring the WASANT paleo valleys back on, you can straight away see that there's areas where we could significantly increase the subsurface distribution of these paleo valleys. But there's also the connectivity between what's been mapped as previously two paleo valleys could potentially be connected. And this is really important because if these things are, groundwater conduits, understanding how the groundwater migrates through these areas, it's a very arid area, and the thickness of these paleo valleys is really important. And that's just sort of just showing how we can really make a better understanding of what's going on undercover with the data set. So we're going to scoot over to, we're in Queensland now. We're looking at the eastern side of the AusAEM1 survey, so just near Georgetown. And you can straight away see that there's these conductive horizons, and they've been truncated by what looks like a fault in the magnetics. They also correlate very well with these conductive, these highly magnetic features here. If we look at the gravity, we see a similar correlation between these highly conductive areas and quite dense rocks. But if we just focus on in this area with the little box on it and have a look at the AEM in greater detail, in that area we have a borehole that's intersected this conductive horizon. And at that point where it intersected it intersected a pyritic black carbonaceous shale. If we look at the magnetics in greater detail there, we see an excellent correlation between the conductive horizon and the flight line in pink here. So we're intersecting this black carbonaceous shale, and it's really helping us build that, understanding that what this conductive feature is that black carbonaceous shale. If we look at the surface geology, that really helps us confirm that, because we've got what's known as the Stockyard Creek mudstone member in that area, which correlates really well with the other geophysical data sets. So what that really helps us do is extend that understanding undercover, because this stuff outcrops in this area, but it's covered in the north and the south. So we can map that unit or similar units undercover. In some areas, we've got over 200 meters of resistive Mesozoic cover, but we can trace that unit down. So we can map that for like 50 kilometers to the north and over 150 kilometers to the south-southeast of where it's mapped here. And what's really interesting is that 150 kilometers to the south-southeast, we have units of the same group come back up to the surface. So it really helps us build that link and confirm that that's that unit extending undercover. Some work that's currently happening is Maddie, who's in the room here, is working on interpreting the AusAEM Northeast Queensland survey, which a lot of these interesting things that we saw here were truncated by the survey boundary. So that'll be interesting to see what Maddie comes up with in that area. And again, this kind of information can really be helpful to mineral explorers, not only to look at cover thicknesses, but help with the targeting as well. Sorry, I know it's getting late. We'll try to rush through this all. So Canning Basin. So we're over the other side of the continent now. We've done a big body of work here. So again, we've got a lot of that Cenozoic cover, but you can strip it all off using the AEM, and we've done a big interpretation there as part of a collaboration with the University of Queensland. And so this was mainly focused on that chronostratigraphic mapping, but looking at features that could be used for underground storage of hydrogen. So what I've plotted on here is the Malua salt isopacks from Thomas and Zand from Geological Survey of Western Australia. And we're just going to look at where the salt is known to occur and some of the features we see in the AEM. So first of all, you can see that there's these nice flat lying features in these areas, and we've got a lot of faults coming up here. We've got a lot of faults up there, so there's sort of a bit of deformation around those edges. When we bring in that Malua salt, you can see that these faults and those zones of deformation correlate really well with the edges of the salt. So we started to see these zones of deformation in the data set. So really flat-lying stratigraphy where the salt is known to occur, but around the edges of the salt, we get these zones of deformation. So what does that all mean? So what we did was, so we'll just look at a couple of these areas in a bit of greater detail. And so you can see through here, there's maybe some folding over here, a bit of subsidence. And so how we've interpreted this is that you've got the salt, where the salt is stable and flat lying, the overlying stratigraphy is all very flat lying and undeformed. Around the edges of the salt, you potentially have salt dissolution, and that has caused those subsidence and these zones of deformation. So that's how we've interpreted that. And so what that says is that we can use AEM as a sort of proxy to where salt could be. And we're currently working in the Officer Basin at the moment. Alexander Sen from my team's working on that. And we've seen some really cool stuff in the Officer Basin where there's salt diapirs and salt walls. So I'm not going to present any of that now, but I definitely recommend keep your eye out for that when we get around to releasing that. So this is pretty much getting close. Sorry, Vaughn. But Eastern Resources Corridor. So we're now in the sort of southwest of Australia. We've got the Curnamona Craton, which you all know is very prospective for base metals and some precious metals in the Deramerian origin as well, and base metals as well. But these large provinces and cratons and origins and whatever you want to call them, are covered. We've got the Lake Eyre Basin, the Eromanga Basin, the Murray Basin. So we can use the AEM to see through these. Straight away, you can see those conductive basins. There's conductive sediments in the basins. We can do our interpretation of that. What's really interesting in the Murray Basin is that there's rare earth deposits in some of these units, so that the Loxton Perilla sands and the Pathway Formation in the Murray Basin, they host clay-hosted rare earth deposits, and so we can actually map those units undercover, how they extend away from their outcrop, and also that can really help for that exploration, but it can also help for groundwater mapping as well, because this area has got a lot of agriculture. So understanding the groundwater, where salinity is and where aquifers and aquitars exist, is also important. So if we just strip off that within Cenozoic. So now what we're looking at is we're looking at everything older than Cenozoic. So here we have, that's the base of the Murray Basin through there, where it could be interpreted. Up here we have we had some Delamerian NDI, MinX, CRC, NDI drilling, and the AEM interpretation was used for targeting, and they intersected the base of the Cenozoic and the top of the Paleozoic at within meters of the interpretation, so under 10 meters. So that was an excellent win for the interpretation, just to show how it can be used for drill hole targeting and looking for basement highs. And also, what's really interesting here is that we've got the Kairmantu group, which is, there's a lot of copper, base metals in the Kairmantu. We've got the Stall zone, there's a lot of gold down there. And we can actually get a better feel for the depth or the thickness of the Murray Basin and the depth to those prospective rocks. And as the exploration is moving to deeper areas in these areas, this kind of data set can really help explorers understand the thickness of the cover over those prospective rocks. Similarly with the Konamono Craton, so we could just map those Lake Eyre Basin and the Carpentaria, the Errebanka Basin in that area. So it's really just gives us a better understanding of the depth to these prospective geological features. Just to get an example, so the Geological Survey of New South Wales were really interested in interpreting their COBAR AEM survey. So they reached out to us, and what we did, we designed a bespoke version of our workflow to capture some of their features and some of the attributes and the sort of the color symbology that they wanted. And this is just an excellent example of the adaptability of our workflow and how it can be, picked up by, other collaborators and other partners, stakeholders to really sort of help us build that national scale interpretation of airborne electromagnetics. I really recommend having a look at this report as well. It's got some really interesting information about AEM interpretation in it. So this is going to be my final example. So just sort of some of the applications of all of this. So really, why are we doing this? So as I said, everything goes into the ASEG database. The ASEG database, we extract all those depth estimates for cover modelling. So here's just some examples of some regional cover models. We've got the Tennant Creek to Mount Isa cover model and the Eastern Resources Corridor cover model. But these ASEG data points have also been used in these national scale cover models that have been created by our groundwater team. These ones have that layered geology draped on it as well, which was done by the integrated geological mapping team. And so what this is showing that all this data isn't just, we're not doing it just for fun. It's feeding into these cover models that really inform about the depth to certain stratigraphic units or certain chronostratigraphic interfaces. And so, how's that valuable? Well, let's just do a little case study. So here's the Mesozoic cover model, and there's the base of the Mesozoic, and there's the base of the Neoproterozoic cover model. So if we imagine we've got a zinc, lead, silver deposit underneath the Mesozoic rocks, if we use the Geoscience Australia's economic fairways to look for that deposit under the Mesozoic rocks, what this is telling us is highly prospective over a large area to go into this area and develop that deposit. If we've got that same deposit underneath Neoproterozoic rocks, because of that thicker cover, it's actually not very, it's not very economical to go into that area and develop that deposit because of that thickness of cover. So that's just an example of, how these data sets that, we're capturing can be used. And look, that's it. I'm sure you're all getting tired. It's very late. But yeah, so really where to next? So keep your eye out for this data set. It's going to be published soon. The Officer Basin, we're also working on that to get that out. And just kicked off, but the northeast Queensland as well. So yeah, there's still plenty of work to go. It's ongoing, and yeah, thank you very much.
Seb, questions, comments, Seb, online within the room?
So beautiful talk, beautiful illustrations, lovely slides.
Thanks, Richard.
How long does it take you to do, say, a 250,000 sheet or a million sheet, something like that?
It's a very good question. So I have actually made a calculation of that based on a whole bunch of different interpreters, a whole bunch of different interpretation styles. It ended up coming out really generous. I know if it was in a perfect world, you could interpret, like I could probably interpret 6 AEM lines. So what's that, like, I don't know, a few hundred kilometers in a week. But when you take into account like real world factors, like, you know, people get sick, people can be affected by natural disasters, and all of this actually goes into that. It really takes that out a lot. So I can't tell you exactly, you know, it's going to take a 250K sheet. Look, you could probably do a 250K sheet if that's all you were doing, you know, 8 hours a day. You'd probably do a 250K sheet in like, I don't know, I would say maybe a bit less than a month.
600 to 652.
Yeah.
250K sheets in Australia.
Yeah, and I think what really makes it take long is that we're not just quickly just drawing lines and saying that's a basis center. We're capturing stratigraphic units, the stratigraphic unit numbers, all consistent with ASARD. We're capturing the confidences of those units occurring in those areas, confidence of the line placement, comments, all kinds of stuff. So it's sort of, it is a bit of a joint interpretation, because we're looking at the mag, we're looking at the gravity, surface geology, holes, everything sort of comes in. So there's a lot to do, and you come into one area, you could smash out like 10 lines in a week, and then you go into the next area and you just be sitting there scratching your head over one line. So it really depends on how the geology plays, you know, like if it's, you know, playing nicely and you got a nice, you know, layer cake, you know, sedimentary basin, it might be pretty quick. But if you move into some of more of these deformed, especially if there's not much of a conductivity contrast, then it becomes really difficult to, you know, actually draw a line, or even if you should draw a line, and then you got to really do a bit more mental gymnastics. So it really depends on the area and the complexity of the geology.
You only work on the AEM program, not the previous ones, like
No, we do. So in that Eastern Resources Corridor, that's got the Frome in it, okay, and it's also got the Mundy survey, which was flown for the Geological Survey of New South Wales. So yeah, there are some holes in the AusAEM that were strategically put there because there was an existing survey. So we'll do what we can with what we've got, sort of.
Yeah, well, in the Uncover agenda, of course, the nature and the things the top priority.
Yeah.
And AusAEM was part of those top priorities acquisition. So it's beautiful to see this go.
Yeah.
Thank you.
No worries. Thanks.
Questions from online.
Sure.
Comparison between AEM models and ground truth where available is remarkable. What constraints were used in the inversion is question 1. And question 2, are the workflows, for example, GitHub reps, available for industry to use?
Yeah. So for the first question, I cannot really comment on that. I would prefer the geophysicists who did the inversions to actually comment on that.
Is somebody online? Do we have Raven or Newson online? Because it's a really important question.
Yeah.
No, all right. Sorry.
But yeah, we can take that on notice. So I'm happy to have a chat with the geophysicist and get back to them. At the second question, do you mind repeating, please?
Are the workflows, for example, GitHub repositories,
yeah,
available for industry to use?
Yes, correct. So for that online graphical user interface, we do have a GitHub repo, and that is all accessible to the public. So the sort of the back end code for the graphical user interface is available on GitHub, and it can run standalone as well. So you don't actually have to use the online graphical user interface. You can actually just go to the GitHub, get the code, and there's instructions. It's all documented, so you can run all of that without even using the graphical user interface as well. So yes, that's all available online. That workflow, so that conversion part of the workflow with that graphical user interface, that also has like a really detailed like a user guide and metadata statement and stuff like that. It can be downloaded with inputs that are required, and it sort of works in collaboration with that other document, which is the sort of the grander workflow as well. Which you know, if people are interested in using it and they have any questions, I'm happy for them to reach out to me. Thank you.
Any other questions? Lots of thanks. Great slides. Are there any other questions from in the room?
So I very much like the idea of having the information behind the line work. So that, to my way of thinking, makes me think of GIS, but you're in 3D. So is it possible for me to download your line work and to bring it into my 3D platform of choice and essentially integrate it?
So it's a good question. So we typically use GoCAD here, and GoCAD has a Mira Geoscience plugin that has a 3D GIS, and so we've developed new sort of 3D formats that can go into GoCAD, and we can use the 3D GIS to say filter for a stratigraphic unit or basis Cenozoic or something that's done by this interpreter, and that can all be filtered and used just like a GIS. But as far as, I can't really speak for many other software packages, but I can confirm that what we do is we also release it as a flat table, which has vertex and segment ID. So you can, so when it goes to a table, you know, you're basically creating points for each row. But because we maintain that vertex and segment ID, it means that you can stitch that back into line work when you go into a different software package. So there has been, you know, that has worked for Leapfrog, Petrel. We can do it in GoCAD as well. So I'm sure if you have a 3D software package that can handle import with this is the vertex and this is the segment ID, it will stitch it all back into a line. I'm not sure how, I can't speak for each different software and how they handle their attributes, but you know, that you will be able to get that into 3D as like long as you do the XYZ vertex segment ID. But you can also, if say that doesn't handle the attributes, so you're not seeing the stratigraphy or anything, you can still use it in a GIS. So you can just like plot XY data. It will just be a whole bunch of points along the line. And you can sort of, you know, just put a color stretch on that for depth or whatever you want. And then you can just interrogate that just like any other GIS software or shapefile, for example, where you can look at, you know, oh, I'm really interested in this stratigraphic unit, and then, you know, query for that, and then it'll just be selected, and then you can look at the depth to that. So you can do that in 2D GIS. You can do it in 3D GIS, but this software is a bit different, different software versions and stuff.
Thanks.
Yeah. Questions? You mentioned how long it takes.
Yep.
You thought about, do you think there is any part of this workflow that can be automated? And if any work done in that, I don't know, so once you've done a large portion of the data and you've interpreted, you can, is it viable to feed that into a training and neural network?
It's an excellent question. I'll touch a little bit on the first bit about the automation. So as far as drawing lines, that's all manual. That's how we do it in using this workflow. There are parts of the workflow that are automated. So a lot of that conversion stuff that I was talking about and putting things, doing validation. So for example, like we with the stratigraphic units, that's all automated. We can validate against the Strat Units database, and it gives us reports saying if typo here and all that kind of stuff. So there are parts of the workflow that are automated. But on your second question, I think you're more so about like, instead of us click, can we just, automate that? So there was work by John Wilford and others a few years back to take this exact interpretation, use it as a training data set for neural networks, convoluted neural networks to create, auto pick. Yeah. So the idea there was not to do the whole suite of chronostratigraphic boundaries, was just the Cenozoic, because the Cenozoic is what I prepared earlier. Oh, where is it? So the Cenozoic is the closest to the surface, and so here we have a human pick, I think. Where is it?
The black line.
Yeah, the black line's a human pick. And then the pick from the convoluted neural network was this pinkish line.
It's not too bad.
Yeah, so what we found there was like, we need to throw a lot of training data at it. It's going to, we can only get it to work for that, that upper level one. But it was really just a pilot study. It's not something that we don't use. We did look into, so I've created like a whole bunch of lines for training data set across WA. We're thinking of, throw that training data at this model and seeing what it does. Straight away, it started having issues, because what happens is, say you've got a big polygon on a surface geology map saying that's Cambrian outcrop. When I'm going along the line, I'm going through that area, and that Cambrian outcrop is actually incised by a whole bunch of little channels and stuff. And so you get all these little Cenozoic alluvium channels all over it. And while I'm doing my interpretation the way I would, I'll be drawing these little channels and stuff everywhere. But this thing is not just training off like our data, but it's also using, like the valley bottom thickness and the weathering intensity and the surface geology, for example. Now that surface geology will be saying, here's a big polygon, but the training data set saying there's all these little incised things across it. So it's like, well, what do I do here, And so there's issues with scale. I think maybe on a local scale where you use training data from a very similar sort of area and then predict into a new area, it's going to work better. But when we take the state of WA, where you've got like Archean, Traton down there and Canning Basin over there and everything else in the middle, it's going to struggle.